Today we're talking about sequences. You have to talk about sequences before you can talk about series. I have these notes here for you to read through, and I'm going to kind of read through them with you today, parts of it at least. A sequence is just a list of numbers in a way. Okay, so for example, you could think of numbers 1, 2, 3, 4, 5, etc. as a sequence. How is it a sequence? Well, this list of numbers follows a continuing pattern. The pattern in this case is just to increase by 1 each time. But you could have any kind of pattern. The numbers in the list are called terms. So each one is a term of the sequence. The number 1 is the first term of the sequence in this case. So we often, just as we often in algebra refer to very unknown numbers as x, with sequences, we often use A's and B's. There's an order to these numbers. Instead of giving them each their own letter, we say A1 is the first term, A2 is the second term, and so on. And in general, the nth term of the sequence, the nth number, is called the A sub n. Now, in this case, since I'm just using the natural numbers, 1, 2, 3, 4, 5, and so on, notice that the subscript is exactly the number in the sequence. So if I want to know what the 100th term in the sequence is, A sub 100, I know it's just going to be 100 because in each case the term is equal to the subscript. Okay, a lot of times when we're trying to understand a pattern in a sequence, it's all about identifying what that nth term is. Here is the sequence of even natural numbers, 2, 4, 6, 8, 10, 12, and so on. Okay, they make the observation that because each of these is an even number, it's actually equal to the corresponding subscript doubled, right? So A1 is 1 times 2, which is 2. A2 is 2 times 2, which is 4. A3 is 3 times 2, which is 6, and so on. So the nth term would be 2n. So if I wanted to know what the 50th term in the sequence was, I would do what? That's right, 2 times 50, which is 100. If I wanted the 100th term in the sequence, we know that's going to be 2 times 100, which is 200, and so on. The 300th term would be 600. Okay, and if I asked you which term has a value of 600, you would say what? 600 divided by 2 is equal to the 300th term. Okay, so whether you're given the value of the term or the position of the term, you can get the other. All right, so a lot of working with sequences is going to be determining that relationship. Now, the sequences that we're interested in are going to be infinite. That means they go on forever. And that's the reason why after the 2n here, we have the ... the ellipses, because that tells you that it's going to go on without end. So here's an example of a sequence that's actually part of the sequence of even natural numbers. So 12, 14, 16, etc. We want A sub 1 to be 12, and we want A sub 2 to be 14, and we want A sub 3 to be 16. We want to figure out what would the nth term in the sequence, how could we write a formula for that one? You're going to use your knowledge of functions to come to conclusions about sequences. And well, they are functions, but they're functions whose domain are just the natural numbers, 1, 2, 3. Instead of being a continuous, interval of values in the domain, we're just going to have integer or natural number values that we're plugging in. So you can kind of analyze it like you would if you had a function that you knew went through the point 112 and the point 214 and the point 316, I'm using the position as the x value, and then I'm using the actual term as the y value. So if I told you there was a function that went through 112, 214, and 316, would you be able to describe that function for me? If I asked you to find the equation of a function that went through 112, 214, 316, could you do that? Yeah, slope, exactly. What would the slope be? It would be 2. Good. So thinking in terms of y equals mx plus b, if you know the slope is 2, then all you would need to do is figure out the y-intercept, right? B, and you'd have the equation. So plug in one of the values, like for example, 12 and 1. You have 12 equals 2 times 1 plus b, and you get 10 equals b. The equation of the line would be y equals 2x plus 10. All right, now remember, I was using as the x, I was using the position. And so the position we refer to as n. So instead of an x, I'm just going to write an n. And y is actually the term of the sequence, which we call a sub n. So in the case of a linear relationship in a sequence, which you can tell this one is a linear relationship because we're going up by 2 each time, you could actually find that representation of that sequence, that term of the sequence, by just using your knowledge of how to write the equation of a line. You could also notice that if there were a term in the sequence a sub 0, what would it have been? If we had gone backwards from a1, what would we have gotten there? We would have gotten 10, right? Good, because we were going up by 2 each time. So if you work backwards in the sequence, then you're going to go down by 2. So that's the same as finding a y-intercept, because y-intercepts are when x is 0, we want to know what y is. So another way to get this would just be to say, okay, the sequence is linear because it's going up by 2 each time. And the starting point, if we had had a 0th term of the sequence, was 10. So we could have also gotten that information that way. So for example, if I had given you the sequence 23, 27, 31, etc., okay, then what would be an equation that would represent a sub n? A sub n would be equal to what? Okay, good. So you can either use the line approach, and you can say, okay, it goes through the point 123 and the point 227 and go from there and find the equation of the line. Or alternatively, you can just say, well, each time it goes up by 1, each time the sequence progresses by 1 term, we're going up by 4. And then if there had been this was the first term, second term, third term, if there had been a 0th term, it would have been 4 less, which would have been 19. So we would have 4n plus 19. All right, but that only works for linear type sequences, which are also called geometric sequences. And we'll get to that later. But that's a good thing to know, and we're going to need it, this will be helpful for you. But right now we're just kind of exploring working with sequences in general. So they might not be linear. In fact, a lot of them will not be linear. So let's look at some other examples of sequences and how we actually denote them and work with them. All right, so if you see a sub n, b sub n, c sub n, d sub n inside of the little curvy brackets, that's telling you that you have a sequence. So this is sequence notation. Okay, let's list some of the terms of a sub n if the rule for a sub n is that the nth term is equal to the square root of n. So the first term is going to be the square root of 1, which is going to be 1. The second term is going to be the square root of 2, which doesn't simplify. The third term is going to be the square root of 3, which doesn't simplify. What would the fourth term be? 2, yeah. And the fifth term? That's right, square root of 5. And we can just put dot, 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 or often you will see people put the formula for the nth term in there, but you have to end with a dot, dot, dot to indicate that this sequence goes on forever. All right, now let's look at B, the sequence B. So the B sub n's. So now we're focused on this formula here. This is an interesting type of sequence because of what happens when you raise -1 to the n plus 1 power. All right, so off to the side here, I'm going to write out what we get because it's a little harder to see this time. So we start with n equals 1. So in other words, we're finding b sub 1. We're going to get -1 to the power of 1 plus 1 times 1 over 1. Okay, so what's that going to be equal to? Well, -1 to the second power is just +1 times 1 is just going to be 1. So the first term in this sequence is 1. Now let's look at what happens when n is 2. So we're looking at b sub 2 here. So we're going to have -1 to the power of 2 plus 1 times 1 over 2. Well, -1 to the third power is a negative. So we're going to get what? Good, -1/2. What's the third term? N sub 3, B sub 3 going to be? Good, +1/3. And the fourth term? Good, -1/4, and so on. So this is actually an example of what's known as an alternating sequence when you have the sign alternate like that. Okay, let's look at the C. First term in the C sequence is 0. Good. What's C sub 2? Good. C sub 3? Good. C sub 4? Good. And so on. Okay, so what did you get for the first 4 terms of the D sequence? Good. So we're going to get just alternating ones and negative ones. That's another example of an alternating sequence. Okay, so these two are examples of alternating sequences. This is another way we could write the sequences, some of the sequences we were talking about. Instead of putting the a sub n and the b sub n in there, you will just put the formula for the nth term, but on the outside we will have these things, the index n or I, which tells you what to plug in for each term, what the minimum n value is where you start, and to go on forever after that, increasing by 1. It is possible to have a sequence like Andres was asking, what happens if the sequence isn't defined for n equals 3? So you might have a sequence where the formula is not defined for n equals 3, but you don't start the sequence at 3. Maybe you start the sequence at 4 or another natural number value. So you would indicate using the index. All right, let's go ahead and look at these two sequences, and let's see if we can figure out the nth term of them. In other words, the formula in terms of n for the sequence. So when you look at A, does anything stand out to you? Any kind of patterns that you notice, and there may be more than one? Okay, very good. It's an alternating sequence. So if it's an alternating sequence, you know you're probably going to have -1 to either an n power or a -1 to an n plus 1 power because it's alternating. Okay, and yes, very good. It does have perfect squares in the denominators. And when you notice something like that, it's not a bad idea to rewrite the sequence with that observation built in. For example, 1 and then 1 over 2 squared, and then 1 over 3 squared, and then what, -1 over 4 squared, because that's going to make it even easier to figure out what the nth term is. You also want to ask, can I write this first term as something, as a denominator squared?
1 over 1 squared.
Very good. We can write it as 1 over 1 squared. So that's good. So every single term fits that pattern. All right, now what we would like to do is to correlate this to the n value 1, the n value 2, the n value 3, and so on. Okay, so we want to, what do you notice? Where do you see n? You see n appear in each denominator, right? Being squared. And then, yes, as far as the alternating goes, it depends on whether the negative shows up in the even terms or it shows up in the odd terms. So in this case, it shows up in the even terms. When you have even terms that need to be negative, you're going to need to use the n plus 1. So that way, when you raise the -1 to the, say, 2 plus 1 power, you're going to end up with an odd power that makes it negative. So if you had odd terms that wanted to be negative, you would have to use the -1 to the n. So what is, putting those two ideas together then, what would the nth term look like in this sequence? We're going to definitely have the 1 over n squared for sure in there, right? But we need to multiply it times. All right, so we have -1 to the n plus 1 times 1 over n squared. Or you could write it as just -1 to the n plus 1 over n squared. Okay, at home, see what you can come up with for part B. Okay, let's take a look at how you're getting that. Good work. All right, so first of all, in the denominator, we appear to have perfect squares. Looks like, or not perfect squares, sorry, powers of 5. And then in the numerator, we appear to have what? Perfect cubes. Yeah, that's how we would say that, perfect cubes. Perfect powers of 3. So in the numerator, we're going to have 1 to the 3rd power, and 2 to the 3rd power, and 3 to the 3rd power, 4 to the 3rd power, and 5 to the 3rd power. And then in the denominators, we have 5 squared, 5 cubed, 5 to the 4th, 5 to the 5th, and 5 to the 6th. Now what you want to do is think about, this is supposed to be your term A1, so your n value is 1 here. This is A2, your n value is 2. And you want to relate that value of the position to whatever is changing in the sequence. So what's not changing in the numerator is the 3. That's going to stay the same, but what's changing has to be related to the n values. And in the denominator, what's not changing is the 5, but what is changing is that exponent. So we're going to have to relate that to n. All right, so in the base of the numerator, the 1, the 2, the 3, the 4, these are exactly equal to the number n each time. So I can say that's going to be n to the 3rd power in the numerator. And in the denominator, it's n, right? It's 2, 3, 4, 5, 6, not 1, 2, 3, 4, 5. So you ask yourself, how is this different than n each time? So in each case, this power is just 1 more than n. So that's going to be 5 to the n plus 1. Okay, so that's our basic introduction to sequences.